There are two types of Friedel-Crafts reactions: Friedel-Crafts alkylation and Friedel-Crafts acylation. Let's start with the alkylation first. In this type of reaction, you start with benzene and an alkyl halide. The alkyl halide can either be primary, it can be secondary, or it can be tertiary. And we're going to use a catalyst with the reaction in order to generate our electrophile. There are two types of catalysts that we can use: aluminum catalysts and iron catalysts. The aluminum catalysts are more reactive in this type of reaction, but we can still use the iron catalysts in there. The reaction is going to proceed by a regular electrophilic aromatic substitution, and your product in this case is going to be a substitution of the hydrogen on the benzene. So we're going to start with the hydrogen on the benzene here. And as usual, the hydrogen will be substituted here by an R group. The difference in this reaction is that you are creating a carbocation. This is going to be your electrophile. That carbocation is due to the reaction of the alkyl halide with the catalyst. So once you create the carbocation, you're going to end up having a primary, a secondary, and a tertiary carbocation. Primary carbocations, they are not stable. So whenever you form a primary carbocation, they can't stand on their own. They have to remain in their complex form. Compared to a secondary or a tertiary carbocation, these are stable and you can form them easily. So let's have an example in there. If our alkyl halide is an ethyl halide, it's made up of two carbons in this case, then these two are going to react with each other. We agreed that with electrophilic aromatic substitution, you have to react the reagents first in order to make the electrophile. And once you make the electrophile, then you react the electrophile with the benzene. So we're going to take the alkyl halide and the aluminum chloride and react those together by a Lewis-base Lewis acid reaction as usual. So the lone pairs on the chlorine, this is going to be our Lewis base, will add to the electrophilic site or the electron deficient site of the aluminum. Do the electronic configuration of aluminum like we did for the iron. You're going to see that aluminum has an empty p orbital. So there is a place for electrons in there that is going to make the aluminum a Lewis acid. So it can accept electrons from a Lewis base, and you're going to create a complex in this case. The chlorine will lose electrons, the aluminum will gain electrons, and this is going to be your complex. And this is the new bond that you formed between the chlorine and the aluminum in there. Now, here's the thing. I know that the AlCl4, this guy over here, is a good leaving group. But if it leaves, I'm going to end up having a primary carbocation. And we know that primary carbocations, they do not exist. So this is why you have to leave that complex in its form, and you're not allowed to break the bond between the carbon and the chlorine. So this whole thing now, you are going to take it and react it with the benzene. The reaction is going to go by an electrophilic aromatic substitution where the benzene is going to act as a nucleophile in there. And then the carbon that is connected to the halogen, this is your electrophile. This is the partial positive carbon. So the double bond is going to open up, take the carbon, and now the leaving group is going to leave. This is very important. So whenever you create a complex up here, you have to check what type of carbocation are you going to form whenever the complex leaves. So look at the carbon that is connected to the halogen and see. If you're forming a primary carbocation, do not allow the complex to leave. Leave it as is, and then start with the electrophilic aromatic substitution in the first step. Allow the double bond to open up, pick up the electrophilic carbon, and then this is going to leave. You're going to break the aromaticity. This is stabilized by resonance where the double bonds can move in there in order to allow the plus charge to move across the ring. You're going to take one of the resonance stabilized intermediates now, and you're going to react it with the conjugate base in the solution, the hydrogen, and regain aromaticity of the benzene, and you're going to end up getting your product. Now, let's say if I add one carbon in this alkyl halide and I start with the 3 carbons instead of 2 carbons as in the previous example. In this case, I will end up rearranging my carbocation. So the R that I'm going to start with is going to be different than the R that is going to be added. And this is one of the limitations of Friedel-Crafts reaction. So as we agreed, we are going to react the reagents together. So we are going to react the alkyl halide together with the catalyst together. The alkyl halide here that I am using is a primary alkyl halide. So start reacting this by doing a Lewis base, Lewis acid reaction. All of these mechanisms you are responsible for. The Lewis acid, this is the electrophilic site from the aluminum. So your lone pairs on the chlorine are going to attack the aluminum and make a complex in this case. You always locate the carbon that is connected to the leaving group. So this is the leaving group over here, and this is the carbon that is connected to the leaving group. If the leaving group leaves, then this carbon will be a plus charge. It's a primary, it cannot stand on itself. But because I do have more carbons that are connected to it, I can simply do rearrangement where I can do a hydrogen shift on the adjacent carbon and change the position of the positive charge from this carbon to this carbon. So here's how you do it. You locate where your carbon that is connected to the leaving group and you look at the adjacent carbon next to it. You take one of its hydrogens and you move it towards that carbon, and now your plus charge is going to be over here. So if the plus charge is here, then it's going to be a secondary. So during the process of the rearrangement, once you move the hydrogen, you can easily get rid of the leaving group, and you're going to end up having your secondary carbocation. That secondary carbocation is stable. It can stand on its own. Plus, of course, the conjugate base. And that conjugate base that we are forming is going to be the one that we're going to use in the third step of the reaction to regain the aromaticity. So now I'm going to use that electrophile and do an electrophilic aromatic substitution. Start with the benzene and that electrophile in there. Double bond's going to open up. Pick up that electrophile. Notice that it picked up the most stable carbocation, which is the secondary one. And then the base, the conjugate base, is going to come take the hydrogen, form a double bond, and you are going to end up getting your product. Let's have another example. If we're starting with a benzene, and we are reacting the benzene with isobutyl chloride in presence of AlCl3. Our alkyl halide here is a primary alkyl halide. Okay, always whenever you have a Friedel-Crafts reaction, always think you are forming the carbocation. So always rearrangement should be in your mind in there. So I'm going to start by reacting the alkyl halide with the aluminum chloride first. So that is going to be step 1 in the reaction. I'm going to form the carbocation. So to form the carbocation, which is the electrophile in this case, so we're going to start with the alkyl halide. Draw your lone pairs. This is going to be your Lewis base. And that Lewis base is going to be reacted with the aluminum, which is the Lewis acid. So this is a chlorine, and another chlorine. Your arrow is going to be from the Lewis base to the Lewis acid. So this is going to be the Lewis acid. And the Lewis acid is going to be the aluminum in there. You are going to create a complex. The chlorine will lose electrons, so the chlorine will be a positive charge in there. And the aluminum is going to gain electrons, so it will be a negative charge. And you have your 3 chlorines in there. Now again, this carbon over here if you allow the leaving group to leave, so this guy over here is going to be a good leaving a group. So if you allow the leaving group to leave, you're going to have a plus a charge on this carbon and it will be primary. We said that primary carbocations cannot stand on their own. This is why you would need to do rearrangement if you have enough carbons on this side. And we do actually. So you look at directly at the adjacent carbon, and on that adjacent carbon, I do have a hydrogen. So the way that you do the rearrangement in this case, you move this hydrogen towards the adjacent carbon and you allow this group to leave. So you are going to end up having now your plus a charge on this carbon because that carbon lost the hydrogen. And you're going to end up getting your tertiary carbocation. So this is a tertiary butyl carbocation plus your leaving group, which is the AlCl4 negative, that is going to act as a conjugate base in the reaction. The tertiary butyl carbocation, this is a tertiary carbocation, and that tertiary carbocation is very stable. It can stand on its own, so I can carry the mechanism of the reaction. So now on the second step of the mechanism, I'm going to start with my benzene now and do an electrophilic aromatic substitution where I am going to open up the double bond. That is going to pick the electrophile. I'm going to end up having, and I'm going to end up having the R group directly attached to the cycle. Now it's no longer a benzene anymore. I broke the aromaticity of the ring in there. Here you go. This is going to be my intermediate, and it's going to be a resonance stabilized intermediate. And then step 3 of the reaction, we are going to take that resonance stabilized intermediate, okay, and we are going to react that with the conjugate base in the solution. That conjugate base is going to come, take the hydrogen, form a double bond, and you are going to end up getting your product. In this case, your product is going to be aromatic, and you added a tertiary butyl group to the benzene, so you got a tertiary butyl benzene. So see over here, I started with an isobutyl chloride, and I ended up doing rearrangement to this isobutyl group, and I ended up getting the tertiary butyl instead. So that is going to be the tertiary butyl group. This means that when I have more carbons for my alkyl halide, always rearrangement is going to happen in order to form the most stable carbocation, the most stable R plus in there that is going to add to the benzene. Another example here, I'm starting with the benzene and tertiary alkyl halide with aluminum chloride. React these two together first and make your complex. And then after that, allow the AlCl4 to leave. If this leaves, then you're going to end up getting a tertiary carbocation. This is stable. You don't need to rearrange. You don't need to do anything. This is stable. So we can take that one and carry the electrophilic aromatic substitution reaction with it. It's a 2-step, and we're going to end up getting our product. For this example, when you react the primary alkyl halide with the aluminum chloride, you are going to make a complex in there. Again, this carbon is going to be a primary carbocation if this leaving group leaves, so you cannot allow it to leave like this. You need to do rearrangement because you have enough carbons on this side. For rearrangement in this particular example, there is no hydrogen on the adjacent carbon. So on this carbon, there is no hydrogen. So I need to proceed the reaction by a methyl shift. So you're going to circle the methyl, and you're going to move the methyl and then allow the AlCl4 to leave. In this case, you're going to end up getting your tertiary carbocation, and that tertiary carbocation is going to add to the benzene by the two-step that we already know in order to form the product. There are other reactions that can produce a carbocation, and all of these reactions you already know from organic one. So if I give you a benzene, and if I give you an alkene and an acid, we said that always react your reagents first, and then create the electrophile, and then react it with the benzene. So you start by reacting the alkene with the acid. This is a simple addition reaction to the double bond. Double bond is going to open up, pick up the hydrogen, and the hydrogen is going to add to the less substituted carbon so that you can form the positive charge on the most substituted carbon in there. Once you create your positive charge, you're going to end up having the HSO4 negative. That is not a nucleophile. This guy over here is a base. Here, that base in there is going to continue the electrophilic aromatic substitution reaction. So the reaction here is going to stop at the electrophile. And now we're going to take our electrophile in there and then add it to the benzene. The electrophile is a secondary carbocation, and that is a stable one. We cannot make it tertiary. So notice here that you cannot do any rearrangement. So the double bond is going to open up, pick up that carbocation in there, and then break the aromaticity, and then you're going to use the one of the resonance structures for the intermediate. You're going to regain the aromaticity back by the conjugate base. So this is the conjugate base in there, and you're going to end up getting your product. Another example, if I start with benzene, and I react the benzene with, let's say, an alcohol. Okay, this is it's a methyl cyclohexanol in presence of an acid. This is organic one. This is a secondary alcohol. And the reaction with the acid is going to go by elimination. This is going to go by E1 elimination, but we are not going to proceed with the elimination till the end. We're just going to make the carbocation. So step number one, you're going to react the reagents together. So we're going to start with the alcohol. And we are going to react the alcohol with the acid. So this is the sulfuric acid in there. We can use either sulfuric or phosphoric acid. OH is a bad leaving group. It's a very bad leaving group. But that OH we can simply protonate. And the HSO4 negative is going to leave. So we're going to end up getting water. Okay, please review the elimination, the E1 elimination in there, plus the HSO4 negative. This guy is going to leave, and you are going to create a carbocation. This is how E1 elimination happens. So with E1 elimination, the leaving group is going to leave. So that's going to undergo E1. Leaving group is going to leave, and I'm going to make a carbocation in this case. My carbocation is a secondary carbocation. And I can easily change that carbocation into a tertiary carbocation by doing a hydrogen shift. So you do a hydride shift, and your new carbocation now, it's going to be a tertiary carbocation. Plus, of course, my base in there, which is the HSO4 negative. We're now going to continue the E1 elimination. So the E1 elimination will stop here at the formation of the carbocation. The reason why, because the reactant that we are doing the reaction with which is the benzene now, it's going to be more reactive than carrying out the E1 elimination till the end. So now we're going to get our carbocation, which is the most stable carbocation, And this is going to be step 2 of the reaction. And we're going to react this with our electrophile. So that is going to be our electrophile in there. This is the tertiary carbocation. The double bond is going to open up, pick up the electrophile in there. Pay attention to the carbons that you are adding in this case. So no longer your benzene is going to be aromatic. And what I am adding over here is the cycle. And on the cycle in there, I have a CH3, okay? And then I'm going to end up having a plus a charge, and I have a hydrogen over here. This is one of the resonance stabilized intermediate. So in the second step, which is step 3 of the reaction, I'm just going to write it over here. So step 3, in the reaction, I'm going to use my conjugate base in the solution, which is the HSO4 negative. So that HSO4 negative is going to come. It's going to take the hydrogen, regain the aromaticity back of the ring, and you are going to end up getting your aromatic benzene. But now what you added on the benzene is your cycle. Plus you generate your catalyst back, which is the sulfuric acid.